this worksheet is on nodal analysis. You just finished learning about mesh analysis. So this is another approach. In mesh analysis, we use the principle of Kirchhoff's voltage law, some of the volts in the closed loop, and wrote our equations for that. In nodal analysis, we're going to deal with current sources. And we're basically using Kirchhoff's current law, which says the sum of the currents entering and leaving a node is equal to 0. Okay? So what we're going to do is learn to write the equations, identify the nodes, learn to write the equations, redraw the circuit, and I think you'll find this pretty easy. Okay? The first thing we need to do in looking at our circuit is to identify the nodes. Of course, as with mesh analysis, you're always going to have a reference node. In this case, it's the ground reference. You will have, when I'm looking at this circuit, I see a node 1 here and a node 2 here. I'm looking at these two resistors in series with this voltage source here, V1. So I can combine those two resistors and make that into a current source. In other words, I'm going to do some source conversions and redraw my circuit. This resistor here, I didn't label it yet, R5, in series with V2 forms another voltage source. This is a 7.33 ohm. And I probably should read these values to you. R1 is 2.44 K, V1 is 42.62 volts, R2 is 8.56 K, R5 is 7.33 K, V2 is 65.15 volts, R3 5.64 K, R4 1.48 K, R6 9.27 K, and V3 61.44 volts. So now then, looking at your circuit, what you're trying to do is identify sections where you can change voltage sources into current sources. I prefer to always do my nodal analysis using the current source form of the circuit to write my equations from. So that's the first thing I'm going to do is identify my nodes and then redraw the circuit. As I was saying before, R2 and R1 in series with V1 make up one voltage source that I can convert. R5 and V2 make up another one. You know, your voltage source form was a series resistor and a voltage. Okay, another one is R4 and V3. So when I redraw my circuit, it's going to look something like this. This current source right here will represent V1 divided by R1 plus R2. So this turns out to be 3.87 milliamps. And in parallel with that, of course, I have my resistor here that represents the combination of R1 and R2. So I'm just going to label this R1 plus R2. Now that value, if you add those two together, it turns out to be 11 K ohms. Then I have another current source. I think I'm going to run out of space here if I don't compress just a little bit. Let's go back. Let me write this 3.87 milliamps here. And come in here with my resistor. And this is R1 plus R2. And its value is 11K. Then I've got another current source that's going to represent V2, 65.15 volts, divided by R5. And then I've got R5, of course, here. Now, this current source, the second one, is worth 8.89 milliamps. And as again, I've said that that is V2 divided by R5. Then I have this resistor here, which I don't have to combine with any voltage source. R3, 5.64K. Then I have another resistor that stands alone, going back to the reference node, which is R6. It's a 9.27K. Then I have another resistor and another voltage source out here. That voltage source is worth whatever V3 is divided by R6. So that turns out to be, I'm just going to point to it with an arrow here, 41.5 milliamps. And this resistor, of course, is the value of R6, 9.27K. Right. So there is my circuit with all my voltage sources of the original circuit converted into current sources. Now, I want you to notice one thing here, that I was using conventional current because I have the arrow in my current source pointing in the direction of conventional current flow. This time, instead of getting a voltage on the right-hand side, we're going to get the sum of the currents entering the node is going to be the right-hand side of our equations. Now, if this voltage source was turned around, this node current here, or this current in this current source, would be pointing down instead of up, and the net current going into this node here would be a negative value because the second current source is larger than the first current source. So here are my nodes, and of course my reference node. Now what I'm going to do is I'm going to write my equations to come up with the voltage at node 1 and the voltage at node 2. What I'm going to do in order to get the, I'm only going to have two equations. See, if you had been solving this particular circuit with mesh analysis, you would have needed 1, 2, 3 equations. You have 3 loops, 3 equations. With nodal analysis, you do your source conversions and you only have to write 2 equations. You don't even need to use simul to get the answers if you don't want to. Because you can easily solve for 2 linear equations with 2 unknowns. Just do it by substitution. I recommend you go ahead and use simul though, because that's quicker and more accurate, probably. All right, writing the equations. Your equations are first going to, we're going to look at the node and we're going to sum all the conductances tied to the node, okay? So for node 1, we've got 11K tied to the node, so we'll take the reciprocal of that, plus the reciprocal of R5. R5 is 7.33K. Plus we would have the reciprocal of the R3, because it's one side of it is tied to node 1. Okay? So my equation will look something like this. 1 over 11K plus 1 over 7.33K plus 1 over 5.64K times the node voltage at node, or the voltage at node 1, minus any mutual conductance tied to an adjacent node. That would be the reciprocal of 5.64K. times the node voltage, or the voltage at node 2. And the right-hand side of that equation would simply be the sum of the currents entering node 1. And that would be, in this case, 8.89 plus 3.87 comes out to 12.7 milliamps. Now, if I do this arithmetic here, go ahead and sum the conductances here. And take the reciprocal here, I get 405 times 10 to the negative 6 times the voltage at node 1 minus 177 times 10 to the minus 6 times the voltage at node 2 equals 12.7 milliamps. So that would be the equation that you would put into your computer program to solve. That would be equation number 1. Equation 2, we're going to have, just like we did in Nodal, the first term for node 2 is going to be the minus 177 times 10 to the negative 6 times V node 1. That's the conductance of the resistor that's mutual to both nodes. And then plus 1 over 5.64K plus 1 over the value of, whoops, I left one out here, didn't I? No, I didn't. I got it. Let's see. I got to have 1 over, yeah, right. I did this one, and this one. Okay, great. I got them all three. All right, 1 over, for the second node, it's 1 over 5.64K plus 1 over 9.27K plus 1 over, I must have that wrong. Let's see. That's 1 point. This value here is 1.48K. Yeah, 1.48K. I wrote that down just wrong to start with. So 1 over 1.48K times the voltage at node 2 equals, there's only one current entering node 2, and that's the 41.5 milliamps, so that'll be the right-hand side. Again, we go ahead and take the reciprocal of these three and add them up. That comes out to 961.1 times 10 to the negative 6 times V node 2 equals 41.5 milliamps. So here's equation number 2 that you put into the computer. Okay, so those are your two equations. I would suggest to you that if you have trouble seeing how I came up with those, that you just simply watch this section several times, and I think it'll dawn on you. Now then, when I plug those equations into Simul, I came up with a V node 1. I'm going to erase this section here. You got those equations, I hope. When I did that, I came up with a voltage at node 1 equal to 54.68 volts. And a voltage at node 2 equal to 53.27 volts. Now then, the only real function of this current source form was to come up with the equations. Once I've got my node voltages, I am going to put them back on the original circuit and use my original circuit to solve for the rest of the voltages and currents. So I'm going to write up here 56.68 volts and 53.27 volts. And now I can erase my equations and my converted circuit because I don't need it anymore. I now have my node voltages. Now then, let's just look and see what we can see right quick. The voltage drop across R3 would have to be the voltage at node 1 minus the voltage at node 2, wouldn't it? Because that would be the difference of potential across that. That turns out to be, let's see, that's VR3. Okay, that turns out to be negative 1.41 volts. So if I say, that means that since 56, did I put those in the right order? No, that's 54, isn't it? 54.68 and 53.27. That's right. So V node 1 minus V node 2 turns out to be 1.41 volts. It's not negative. So right here we've got 1.41 volts. Like so. So that's the voltage drop across R3. If I want the current through R3, what do? Just use Ohm's law. Okay. The voltage drop across R6 is the node voltage, isn't it? So R6 I've already got. Let's look at R5 here. The voltage drop across R5. If I want to find the voltage across R5, I can simply start adding up here. This voltage V2 plus whatever the drop is across R5 has to add up to 54.68, doesn't it? So I'm going to write that equation, then solve for the voltage across R5. V2 plus the voltage drop across R5 equals 54.68 volts. So VR5 has to equal 54.68 volts minus whatever the source voltage V2 was. V2 is 65.15 volts. So the voltage drop across R5 is equal to negative 10.5 volts. That just simply means that the top of the resistor is negative with respect to the bottom of it. 10.5 volts. The same thing can be done with R4 and V3. V3 plus the voltage drop across R4 has got to equal 53.27 volts. We're taking all these with respect to the reference node, of course. If I solve this for VR4, V3 being 61.44 volts, I get VR4 is equal to negative 8.17. That simply, again, means that this voltage source here was greater than the node voltage, so we have to drop something in this polarity across that resistor. Again, if I want to know my current, Ohm's law, V divided by R. So this is 8.17 volts. Probably didn't get that in the picture, did I? it right there, 8.17 volts. All right, now then, what am I missing? I am missing the voltage drops across R1 and R2. What I'm going to do is I'm going to combine those. And I'm going to say V1, just like I did before, plus the voltage drops across R1 and R2 combined must equal the 54.68 volts of node 1. So that just, I've got 42.62 volts right here. So V across the combination of R1 and R2 is 54.68 minus 42.62. So the voltage drop across R1 and 2 combined is 12.1 volts. And I hope that when you do the arithmetic, you get the same thing I did. All right, now then, how am I going to find the individual voltages across R1 and R2? Well, I know I've got a combined voltage across them of 12.1 volts. So I can do it any way else. Well, I've got a bunch of different ways I can do it. I could sum the resistors and divide them into the 12 and get the current and then use Ohm's law on each one. Or I could use the voltage divider rule. I could say the voltage across R1 is R1 divided by R1 plus R2 times the 12.1 volts. That's that old voltage divider rule coming up again. And I could take this value and subtract from the 12.1, and what's left has to be across R2. So there's any number of ways that you can approach finding that last value across, those last two values across R1 and R2. And that, folks, is, all you have to do now is use your Ohm's law to find the currents, and you've got everything you need to know about that circuit. So that takes care of nodal analysis. When you've done your worksheet, we'll finish your test.